Hi everybody, I thought I'll just make a short video about waves, just one more little introduction to waves. Like I said last time, a wave is because of a succession of pulses, and here's an example of what happens to the particle for a transverse and longitudinal wave. So the top diagram is that of a transverse wave. Watch what happens when I start. So here we go. So there's your succession of pulses, there's your wave moving down, and actually what happens is each particle is only moving up and down. They don't actually leave their places and go somewhere else. So that's your transverse wave. And then you have your longitudinal waves where the particles are vibrating back and forth. So they vibrate, or the particles move parallel to the direction in which the wave moves. Okay, so that's your transverse and your longitudinal wave. And then here, just a transverse wave is represented this way. Your wavelength is the distance from one crest to the other. The amplitude is the height of the wave, and it's really the distance from the middle of the wave, the equilibrium position, to the top. So that's the amplitude. Okay, and the longitudinal wave is made up of, so there's your wavelength, but where they come together, that's called a compression. Where they're far apart, that's a rarefaction. And the next thing I'm going to tell you is what happens when you have waves on water coming and hitting a barrier. So it's going to get reflected. So these are called wavefronts. They represent the crests of the wave as they approach a barrier, and then they get reflected. Okay, there they go. So this is like a beam of light. Those are your incident wavefronts. Incident, the one that's falling on the surface, and then you have your reflected wavefronts. Okay, and now I'm going to show you how do you actually draw this diagrammatically. So to learn how to draw this diagrammatically, the first thing you do is, this is your boundary, the surface, and then we draw a normal. That's my dotted line, which is at right angles to the surface. So the black line is the surface, and the first thing we draw is the direction of the wave. So that's the ray. So that's your incident ray, that's your reflected ray, and there's your angle of incidence, should be equal to the angle of reflection. So once you've got both those in place, that's half the battle won. And then the next step is to draw the wavefronts. So the green lines represents the crests of the wave. So the distance from one green line to the next is your wavelength. And notice these green lines are at right angles to the ray. So actually the wave is moving this way. Okay, so that's the direction in which the wave is moving. So that's your incident wavefront. And now you've got to draw similar for the reflected ray. So in the end, your diagram is going to look like this. So the green lines are your incident wavefronts. Those are your reflected wavefronts. And what you have to be careful is, if the wavelength doesn't change, so the distance from one blue line to the other is the same the whole time, as well as it's the same as the distance from one green to the other. So this is quite easy. So this is how you draw a diagram for two-dimensional wave for reflection. Okay, so I hope that made sense.